And there is some background construction noise. So I'll discuss some of the questions uh, related to week 6, which mostly covered some continuation of the backpropagation algorithm and some introduction to autoencoders and their comparison with PCA or principal component analysis. So let's look at this first question. If you have any doubt, just interrupt, uh, whether it is regarding the week's content or anything which was covered previously. So here, I think I have the question is visible to everyone. So here, what they are asking is what will happen when the learning rate is set to 0. Options are weight update will be very slow, weights will be 0, weight update will tend to 0, but not exactly 0, weights will not be updated. What do you think will be the answer? It's a simple question, right? So what is the weight update formula? It is W is equal to W minus eta times the gradient of whatever is your loss function. Let's say W. This is also W. This loss function will be a function of your input and your weights and also the label. No? This can be squared error, mean squared error, or cross entropy loss function. So, and this is your learning rate. So if learning rate is 0, if learning rate is 0, then W is equal to W minus 0. So there won't be any update. These other options like weight update will be slow. That will when will weight update be very slow? When eta is close to 0, but it is not equal to 0. It is some small value greater than 0. And in this case, weight update will be slow. So if your this is your W and this is your loss function and something like that. Let's say you are currently at this point. And this is the place where this is the value of your W for which your loss is minimum. And this is your gradient. So if learning rate is small, you will take very small steps. So the weight update will be slow. Weights won't be 0. I mean, if you're initializing by 0, then the weights will remain 0. But usually you initialize with some random weights, random non-zero weights. Weight update will tend to 0 but not exactly 0. So weight update is exactly like there is 0 weight update because the learning rate is 0. The learning rate is very close to like 10 power minus 10 or something, which is very small value. Then there is almost no update. So then we can say weight update will tend to 0. So it is quite clear that weight update, like there will be no weight update when learning rate is 0. So you always want to set a value of eta greater than 0. Okay. Any doubts on this? Okay, then I'll go to the next question. So here the question is during back propagation through max pooling with stride gradients are also what how the gradients will be, that is what is asked when during max pooling. You have a doubt?
Yes, actually slides are not visible.
Screen is not visible.
Yes.
This OneNote page is not visible.
Yes. No, actually not. For me, it's not visible. I don't know about others.
Okay, maybe I can stop and try to share again.
Yes.
So I've shared again. Is it visible now?
Yes, it's visible now.
Okay, so before you, it was not visible, the first question when I discussed. Was it visible during the first question? You can type in the chat or unmute and say. Okay, anyway, it will be there in the recording so I can check later also. So I think it is visible right now, so I'll discuss this question. So the question is saying during back propagation through max pooling with stride, the gradients are. So I think max pooling was discussed like if you have some inputs uh, like x1, x2, x3. And if here the activation function is max pool, what we will do is it will output the maximum value from x1, x2 and x3. So they are asking how are the gradients uh, for this kind of max pooling. First option is evenly distributed. That means each of these inputs will get the same gradient. It will be distributed evenly. Sparse gradients are generated with non-zero gradient at the max response location. That means if the output of this is x2, then a gradient will be generated only at x2 and the other gradients will be 0. Here there will be some gradient. Differentiated with respect to responses.
Answer may be B. Sparse gradients are generated with non-zero gradient.
Yeah, yeah. That will be the correct answer, right? Because when you do, take the derivative with respect to this, you are getting, like, with respect to, like, if this is f of x, then partial derivative of x with respect to x1 will be 0, with respect to x x3 will also be 0, with respect to x2 it will be 1. So you will get a gradient over here, and here it will be 0. So whatever will be propagated from whatever further layers are there, that will be multiplied by these values. So because only this has non-zero gradient, if g got propagated here, then g times 1 is g will be propagated further back only to x2, not to x1 and x3. So this kind of this max pooling function is very popularly used in uh, like neural network architectures for images, because there what happens is a bunch of features may be learned in this input layer, but if you have to classify, let's say, like here, if let's say there is image of animals, then it may learn some ear, leg, or nose kind of things, and in the forward layer it has to take some inputs and it has to classify over here somewhere, let's say. So what it will do is, if let's say it was cat versus dog classification, how it will learn is maybe the nose is enough to classify cat and dog, the nose part. So it will learn it in such a way that always this value will get maximum and this will be propagated here. Only the nose part will be propagated here, and the classifier will learn to classify the image based on the nose. I'm just giving a rough idea. Somewhat something like this is observed, like how the neural network learns when classifying like images. So there this max pooling kind of comes to use. Okay, any doubts on this? So the answer is the sparse gradients with non-zero gradient at max response location. This is the max response location which has a non-zero gradient. Okay, I'll go to the next question then. gradient of sigmoid function is maximum at x equal to question mark. So what is the sigmoid function? It is this, right? So you have this is 0, this is 1, this is like 0.5 or something. This is here sigma of x and x. Okay. So as x is going to infinity, you can see like gradient is going to 0, and x is going to minus infinity, also gradient is going to 0. Somewhere in between it has non-zero gradient. So the gradient of sigmoid function is what? Sigma x into 1 minus sigma x, right? And sigma x value ranges between 0 to 1. So what is the maximum value of this function? That is what we have to find out. At what x it is maximum. So what is the maximum value of this function if it is between 0 and 1? So this is a quadratic function, right? This is a quadratic function which has a 0 at 0 and 1, and it is downward facing. So the maximum value that it is getting will be at this point. So you can find out like where this is coming if you take this is y into 1 minus y or something like that. Then if you take the derivative, what you will get is y is equal to 0.5. So this is 0.5. I mean, because this is a quadratic function, you know it is the midpoint of 0 and 1. So it is 0.5. That means at sigma x equal to 0.5, the gradient value is maximum. It is this value. It should come out to be 0.25. So at what value of x is sigma x equal to 0.5? It will be at x equal to 0, right? Because when you put x equal to 0, what you get is what? Like sigma of 0 is equal to 1 upon 1 plus e power minus 0, which is 1 by 2. Okay. So gradient of sigmoid function is maximum at x equal to 0. Yeah. So that was like, you just had to look at the function. If you know what the sigmoid function is and some basic calculus, we can easily find out the answer to this question. Okay, so I'll go to the next question if there is no doubt in this one. So here what is asked is find the gradient component g of this function. So there is some previous layer, it goes to the layer where you do e power x, and then whatever output you get some y, it goes to the next layer, and the back propagation gradient that is passed, it is given like from this layer you get a gradient of 2, and from here to here you get some g, and what is that g that is asked. Okay, so how we will do this? So let's see. So this was, so from here let's say only you get x, and here you have some g of y. Okay, so this we can say some del g y by del y, that is equal to 2, but what we want is del g y by del x, so that will be del g y by del y into del y by del x. This is given as 2 that we got from here, into del y by del x, so 2 into e power x by, so this will be the derivative of e power x with respect to x is e power x, so it is 2 into e power x. Now the value of x is given as 2. So what you get over here is, so maybe I should have written here x. It is some function of finally x, this whole thing. Okay. So del g of 2 and del x will be 2 into e power 2. So it is c. Yeah. So if the input had been something else, it would, x would have changed. Or if the gradient propagated would have been something else, then that would have changed. Yeah, 2e squared. Yeah, you have a doubt? Yeah, Varsha, you have raised your hand. You can unmute and also ask if you have a doubt.
Hello, sir.
Yeah,
Sir, the option is option C or is correct, sir. To
yeah,
eat correct.
yeah. Option C is correct.
How about it?
Okay. Okay, so there is no doubt in this part. Then I'll go to the next question. So here the question is, what is the similarity between an autoencoder and principal component analysis? So both kind of enable like dimensionality reduction. In autoencoder, you have a neural network kind of architecture where you have like reducing dimensions in your forward layers, and then you decode it to increasing original dimension. If this was original dimension was some d1, then this is also d1, but d2 and d3, it will be something like this. And if your input here was x and this is x dash, then your objective is to learn your weight such that you minimize this reconstruction of the this is the squared error between what your input was and what your output was. So that is your autoencoder. In principal component analysis also, you want to do the same thing, but instead of having a complex architecture, you try to find out what is the like linear transformation I can do such that if I try to reconstruct it back, then my error is minimized. So what is the similarity between autoencoder and PCA? That is what is asked. So he is saying both assume non-linear systems. So only autoencoder is having these non-linear systems because of non-linear activations that you can put in your hidden layers. But PCA only considers linear transform. The subspace of 8 matrices. So PCA won't have so many matrices for each of the layers. It will only have one square matrix. Both can assume linear systems. So although this architecture is uh, has non-linearity, it accommodates non-linearity, but it can also like mimic the same linear system also if you just use one layer and no non-linear activations. So C looks like the correct answer. Someone has raised a hand.
Hello.
Yeah, yeah.
Hello, sir.
Yes.
Sir, I have one question actually. The difference between LDA and PCA, sir. Actually, both are used for dimensionality reduction.
Uh, so in LDA, I think you try to find the direction in which you have maximum uh, kind of difference in your what to say you do it for binary classes, right?
Yes, yes. Actually, for the distance between something called intra and interclass variance or
Yeah, yeah.
something.
So there are two
Uh,
classes, and you try to find the direction in which these two classes have like kind of maximum variance. But
Correct, correct.
in PCA, the class label is not given. You look at the entire data
Uh,
and you try to
uh,
look at the direction in which there is maximum variance.
like supervised and unsupervised.
Yes, yes. PCA is unsupervised. Like autoencoders are also unsupervised because you're not giving any labels. Similarly, PCA
Okay.
is also unsupervised.
Sir, I have one more question. Maybe it is not related to this.
Yeah.
Shall I ask?
Yeah, yeah. Please ask.
Actually, in both LDA and PCA, they'll use eigenvectors and eigenvalues.
Uh-huh.
But actually, I don't know why actually eigenvectors and eigenvalues are required.
Why are they required, you're asking?
Yes, sir. Actually, I don't know. I've studied actually, but I don't know exactly to define what is eigenvector and eigenvalue. I know how to calculate, but I don't know why something they'll say orthogonality and something and all. But I'm not able to define it if they ask what is eigenvector and what is eigenvalue. Why do we use it in dimensionality reduction? So that is what I don't know actually. If you can able to explain, please, it would be good, really helpful.
Okay, so I'll try to explain briefly. So basic definition of if you have some matrix A, then uh, some vector, let's say E, and this is n cross n, and E is n cross 1. Then if this E satisfies this property that A times E is equal to lambda times E, where lambda is a scalar, then lambda is the eigenvalue and E is the eigenvector. So this is the basic definition. If it satisfies this, then lambda is called the eigenvalue and E is called the eigenvector. Is this part clear?
Yes, sir. Actually, this equations and all I know, but the thing is that how eigenvalues and eigenvectors reduces the dimensions from n dimensions to two dimension or one dimension. How they will be helpful in that case?
So how they are helpful is what arises is when we try to like minimize the reconstruction error using linear transforms.
Hmm?
It turns out that when you project, so A is a what happens is you compute the covariance matrix of your data.
Yes, sir. Yes.
Let's say there is this covariance matrix and it is n cross n. So this covariance matrix is symmetric.
Hmm.
Okay. So for symmetric matrices, for any symmetric matrix you take, and if you compute its eigenvectors, they will be orthogonal. The eigenvectors for a symmetric matrix will always be orthogonal. And when you project your data to these eigenvectors, then if you project it to the eigenvector with the highest eigenvalue, then you find that uh, projecting in that particular direction of the highest eigenvector, let's say it was even, then projecting your data on even direction gets the maximum variance. It turns out that if your data was something like this, then even direction is this. I think there is one question related to that. This question. Hmm. Ah. So here it is asked, which of the following could be the direction of projection using PCA if the data points lie on the locus of the curve shown in figure. So there is some curve. This is the curve. This is the curve. So what happens is, this D is a direction of uh, you can say maximum eigenvector. The eigenvector is maximum eigenvalue.
So, where in which the direction it maximizes the eigenvector and the variance, there it will give the dimensional reduction. It will reduces the features.
So
That's how.
you project your data to all your points to this.
Hmm.
So what will happen is, if you look at this, if this is the direction, then all points will lie on this when you project it. Similarly, you will look at the next direction, then next orthogonal direction, which is perpendicular to this. So next orthogonal direction will come on this one. So then you will project your data onto this also. So if you consider these two directions, then you will get your data in some arrangement. I mean, in this case, because it is a 2D example, you will again get the same kind of thing,
Hmm.
because you are again projecting in 2D to 2D. So 2D to 2D will again give you the same thing, only the axis is shifted now. But if you see, in like, if you were only to project it on 1D, then this was the direction where you will get maximum variance in this D option.
Okay, sir. Okay. Thank you. Thank you so much.
Okay, so I think we are discussing. Was this question clear? You were saying like both, what the similarity was, both PCA and autoencoder can consider linear systems, but PCA can't consider nonlinear systems because it does a linear projection. Okay. Which of the following is only an unsupervised learning problem? So unsupervised learning problem means we are not giving any labels to the data points. So in digital recognition, you will have images of digits, 1 2 something like that. So when you have to recognize the digits, so you will have to give the label like this image is 1, this image is 2. So this is a supervised task. So this is not. Image segmentation. So in image segmentation, what you'll have is, maybe I can show an example. You can also Google. So if you see, if you just take this image, then if you see the original image will not have these boxes and colors. There will be normal people, but the area of the car has been segmented. So that is the task of image segmentation. The people have been segmented in different colors, like that. If you look at this image, all humans are segmented in red, all cars are in blue, all trees are in green, all buildings are in gray, and a road is in pink, and maybe traffic signs are in yellow. So that means different labels have been given to these kind of things. Humans have been given some particular label, one. Cars have been given some label too. So each pixel in the image, each pixel in the image will be, if it's a ball, then each pixel in the ball will be given one label, and if it's a bat, maybe each pixel will be given two label, and if it's background, then maybe 000 label is given to the background. So this image segmentation is also supervised, because you are segmenting the regions belonging to different kind of objects. Image compression. So in image compression, what you have to do is, you have an original image, you compress it into some low dimensional thing, and then you expand it again to your original image, and these two images should match. What is similar to what we were doing in the autoencoder, that can be used for image compression. So here you are not really giving any label, you are just trying to reconstruct your input back. So that is an unsupervised learning problem, we can say, right? So this answer is C. Okay, any doubts on this one? There's no doubt, I'll go to the next question. What is the dimension of encoder weight matrix of an autoencoder? Hidden units equal to 400. Constructed to handle 10-dimensional input samples. So you will have, your input is 10-dimensional. So input is 10-dimensional. So you'll have 10 nodes in input, and autoencoder hidden unit is 400. So you'll have 400 here. So there'll be 10. So what is the dimension of weight matrix? This weight matrix that you'll multiply with your x. So if x is 10 cross 1, we can say 1 cross 10. Maybe I'll say, so this will be 400 cross 10, right? So there are 400 rows and 10 columns. But if you have bias, then you will have one more, 400 rows and 11 columns. If you consider bias also. But here, like this can be confusing. What you want to consider as a row and column, because in different books you will find different what is considered as row and column. Because sometimes you will consider this as W transpose X. If you're considering this as W transpose, then original W will be 10 cross 400. So I think this option can be confusing. uh But it can be either of this or this. So there won't be 401 because your bias will be coming from your input side. So yeah, I think C or D either can be right. But A is not right. And B is only right if we are not considering bias. But uh, in the output you may not require bias, but in the input bias can be required. So B also you can like, reject because not accounting for bias. Any doubts in this? Maybe Sir had followed one convention. I am not able to remember if he followed how he followed the convention. But generally in practical usage, I think you only need to like make sure you're multiplying the things in right manner. Okay, so any doubts in this part? Then I'll go to the next one. So here they are asking, let's say vectors A is 2 4 and B is n1 forms the first two principal components after applying PC. Under such circumstances, which among the following can be possible value of n? So A and B are first two principal components after applying PCA. Then what is the property that we know of A and B? That they will be orthogonal, right? Just now some time back we discussed. Because those are eigenvectors of your covariance matrix, and covariance matrix is symmetric. So symmetric matrices always have orthogonal eigenvectors. So if they are orthogonal means this A vector transpose B vector will be equal to 0. So 2 into n plus 4 is equal to 0. So n will be equal to minus 2. So that means this 2 option is correct. Okay, any doubts? Get this question I think we discussed some time back. Which of the following could be a uh, direction of projection using PC if the data points lie on the locus of the curve? So what we discussed was the points are on this curve and you have a 2D data. So with PCA maximum you can project it into 2D, but if you're projecting it into 1D the direction will be this D option because that is the direction of maximum variance. The second direction will be this C, that is orthogonal to it. That you can say the direction of minimum variance. Okay. I'll go to the next question. So it is asking show that while projecting feature vectors to 1D space, PCA selects the projection direction along which the projected data has maximum variance. So we have to show that when we are doing PCA, so we will compute the covariance matrix of our data X, input data, let's say n samples, and this is the covariance matrix. This will be n cross n because of n samples, and you compute the eigenvectors. Then it will be like E1, E2, En because of n. So then the first eigenvector with the highest eigenvalue. We are projecting the data onto this one. So the question is asking, show that when we are projecting the data to E1, then E1 is the direction of maximum variance. So let's assume K is direction of max variance. Then what does that mean? How do you compute the variance? Uh, you'll project your data to K. Let's say project Y equal to K transpose X. Now I'll find the variance for this. So it will be Y minus mu, which is the mean, times phi minus mu, expected value of this, right? So let's say if I had just 1 point, I think I should consider just 1 point. Yi is 1 point, then K hat transpose Xi. So this you can say it is n cross d, or samples, d-dimensional, and each of my eigenvectors will also be d-dimensional. So when I take the projection, I am projecting it into one-dimensional data. Projection of Xi onto this point. So I'll get a what to say, a projection of a d-dimensional kind of point. Now if I have to compute the variance, yi minus mu squared, this will be the variance, right? And this you can write as K transpose Xi minus, but this mu will also be projected, so the mean of this will be mu of y. So mu of y will be K hat transpose mu of x. So this is also mu of y. So you will have K transpose xi minus K transpose mu x. So this will be expected value of K transpose xi minus mu x. This whole thing squared. So this you can transform it as K transpose xi minus mu x, because this will be a vector into K, right? Xi minus mu x transpose K transpose, sorry, K. And now because K, this expectation will be with respect to x. So you can take K transpose out. Because K is this, whatever we have assumed is a direction of maximum variance. So it's not a random variable, it's a constant. We can take that out. So this is the variance of, what to say, x. So now what do we want to do? We wanted to say that this is the direction of maximum variance. So if this is the direction of maximum variance, that means this value should be maximum. Should be maximum for any k such that K transpose K is equal to 1. That is, we are considering all the unit directions. If any unit direction I take, then only for this particular direction K I get the maximum variance. So I have a constraint like maximize K transpose sigma x K such that K transpose K is equal to 1. So if you have any sort of function such that gx equal to 0, then to find the optimal value of x which satisfies this, what you do is you construct the Lagrangian. So if Lagrangian of x comma lambda is minus fx, sorry I have to do this, fx plus lambda gx, and you try to do this. This is called the saddle point of the Lagrangian. So if you look at this, derivative of this by this is g of x. That means g of x equal to 0. That is the constraint that we have. And at the minima, you want this to be 0. So both of them should be satisfied for you to find the minimum value of f of x such that g of x equal to 0. So if you apply the same thing to this, the only difference is we have max here and min here. So the Lagrangian here will be some k lambda minus k transpose plus lambda times k transpose k minus 1. And if you do k equal to 0, then what you get is K transpose sigma x plus lambda k is equal to 0. And this is this. So that means was K transpose sigma x is equal to lambda k. So this is the property of eigenvector. So what we have shown is uh, the maximum variance, whatever the direction is k, that is actually an eigenvector of the covariance matrix. And the eigenvector of the covariance matrix is the direction that we get from PCA. So we have shown PCA selects the projection direction along which the projected data has maximum variance. Was this clear? This is an eigenvector also. I mean, what is the eigenvector is what satisfies this thing. That is what we showed. This maximum variance direction is essentially given by the eigenvector of the covariance matrix. You can go through this proof once. I'll share the notes. I think this part was just showing that this is the variance that you will get at and projecting to in the direction k. Then we wanted to show that uh, what is the condition in the such that this is the maximum variance value. For what k you get the maximum variance. So the k at which you get maximum variance should satisfy this. Okay. So please ask if you have any doubts regarding this part. I think this is the last question I had for today. So you can ask any doubt you have regarding what we had discussed today, this question or anything that was in the lectures, or maybe then if there is time I can maybe show you some code of how to do code an autoencoder in Python or something like that. And that will not come in your exams, how to code autoencoder. But if you're interested, I can show that. No doubts. Okay, then I'll maybe show some code for autoencoder. Okay, so this is an example that we can follow. Mm. So this is the same, what to say, thing that I saw here. Maybe I'll just add a link to this. So here they have used built-in autoencoder using NumPy, which is a library in Python. If you are familiar with Python, then you maybe already know what is NumPy. It is basically used for implementing different kinds of matrix operations. So in Python, as usual, you load whatever libraries that you require or you are using in your code. So you can use this NumPy, import the NumPy library that you will use throughout to implement the autoencoder and the back propagation algorithm and forward propagation algorithm also. So this keras is a package which uh, which is used for deep learning, but here it is only used for loading this mnest dataset. Mnest is a dataset which consists of handwritten digits. Mnest dataset, if you just Google, it is this kind of dataset where you have handwritten digits and each label is given. So from Keras, you can directly load this MNES dataset. It is the most popular dataset that people used for testing their uh, like deep learning models, mainly for image kind of tasks. So when you import MNES from this Keras datasets, then you can just call mnes.load data to load the images. So if you see, if I just run this, so when they do mnes.load, it returns xtrain, which is, if you look at the shape of xtrain dot shape gives the shape 6000 comma 784. So 6000 is the number of samples. Oh, it's 60,000. 60,000 is the number of samples. 784 is the number of pixels. So 784 is actually 24 plus 24, I think. No. How much is 784? 32 plus 32. Right? No, 32, 32 is not 784. 28 cross 28. 28 cross 28 is 784, no? No, 28 cross 28. So it's a 28 cross 28 image that you see here. I think 0, 10, 20, 28 till here. 0, 20, 28. So it's a 28 cross 28 image. And there are 60,000 such images in the training set. And if you see, there is a dash here, that is the labels. So in autoencoder don't need the labels, so they just put a underscore, actually underscore. So for both the test labels and the training labels, they just put an underscore to ignore them. X test dot shape, if you run it, it is 10,000 cross 784. So there are 10,000 samples in the test data. And these are black and white pixels. So I think the original image range will be from 0 to 255. So to 0 to 255, they kind of reshape and they divide it by 255 to make the range from 0 to 1. So I think if I cut this part, paste here, if I run this again, yeah, so if you see, now I imported MNIST, I loaded the data. If I look at the shape now, it is 28 cross 28, 60,000 samples in train, 10,000 samples in test, 28 cross 28 training, testing image dimension, same as training. Now if I look at like one of the values, let's say x train, if I just do max, let's say max, so the maximum value in this x train matrix is 255 and the minimum value will be 0, I think so. So 0 is the minimum value in the x train matrix, and so each image pixel is from 0 to 255 range. So they divided the image by 255 to make it 0 to 1 range, and they reshaped it to, like if you do the call this function on the matrix, then it will reshape it to 784 dimension. That's why when we run this, your xtrain dot shape becomes 784. Basically what has happened is, whatever your 28 plus 28 image was there, you linearized it to 784 dimensional vector. Okay, each pixel is here, so it will be, each pixel here will be like this, then next row will come here, next row will come here, till that the last row will come here. So now you have one vector, because in your autoencoder you want this one input vector which goes to the subsequent layers. So you have your train and test data kind of ready. Now you define your activation functions. So in this they are using sigmoid activation function and ReLU function, and they have two kind of parameters, which is input z and d. And if you see, what it is doing is, it is returning sigmoid into 1 minus sigmoid plus some small value, very small value, if d is true. Yes, there is some doubt. Okay, and if d is false, it is the sigmoid function. So I think what is happening in this is, if d is true, then it returns the gradient at the value of the sigmoid. That means if I call, if I run this, and if I call sigmoid, let's say 0.5, or let's say 0. So sigmoid of 0 should be 0.5, no? So I'm getting 0.5. But the gradient, if I want the gradient, then I should pass 0 and d equal to true. If I write d equal to true, it gives me the gradient 0.25. So I think in one of the examples today only we had seen, where is it, that at sigma equal to 0.5, the gradient value which we get is zero point 0.5 into 1 minus 0.5 is 0.5 into 0.5, that is 0.25. Okay, so the gradient that we get at 0 is 0.25. So this is just the way of like they have written it this way. You can write a separate function also for gradient and for the forward activation function. They just try to include it, like the default value for d is false, so when you directly call sigmoid with any number, it will return the sigmoid function value. If you call it with d equal to true, then it will return the gradient value. Now they are defining the architecture, what they are using. So this act is the activation function. The ReLU activation function, you have a layer with ReLU activation and this kind of shape of it. This will be the shape of your weight matrix. So they are saying out comma in. So out comma in means 1024. So your input shape is 784. This is 784, and then they are kind of projecting it to a bigger thing, which is 1024, and here it is ReLU. Okay, then in the next thing, they are projecting it down to a 50 dimension thing. So now it's coming down to 50. Then they'll project it back to 1024. So here also it was ReLU. Now again back to 1024, 50, and 784, 1024. Again back to 784. So here also ReLU, but here if you see, it is sigmoid. So can someone tell me why everywhere it was ReLU and here it is sigmoid? So I'll tell you why. What is the reason? The reason is, if you remember, the values ranges were changed from 0 to 255 to 0 to 1. So input values x is in the range 0 to 1, and when you do all the transformations, here the ReLU activation range is from 0 to infinity, but sigmoid range is in 0 to 1, and when you want to reconstruct the input, you want to reconstruct it back to 0 to 1 range, and then you will take that squared loss. This is what you want to minimize, the mean square error between the input image and the reconstructed image, x and x dash. So you want the x dash values to be between 0 to 1. So for that you will use the sigmoid activation function. So that is the reason they use sigmoid here. So this is just which activation has which shape, that is what they have mentioned here. I have written it in the form of a list of dictionaries. So how we can call it is, if there's layers, the first layer, if you look at the zeroth layer in a sense, then the zeroth, okay, I didn't, yeah. So if you look at the zeroth layer, it has activation function relu and shape uh, this. So this relu, if you recall, it is a function that you have defined here. So that's why it's saying act is a function. So if I call here now act, then what it is pointing to, it is pointing to the zeroth layer's activation function. Now if I call it with some value, let's say 0, so it's a ReLU, so let me call it with 5. So ReLU with 5 will give me 5, and ReLU if I give minus 8, it will give me 0. Now if you look at 0, 1, 2, 3, if you look at the third layer, which is the final layer activation function, final layer activation function is a sigmoid. Now on this, if I call 0, I should get 0.5, and if I call this with the gradient value, I'll get the gradient which is 0.25. This is the gradient at of sigmoid at 0. Okay, so now let's look at how they are kept. So L is the number of layers. Length of layers means number of layers. This is some empty list in which we want to collect the error for 30 epochs. It means 30 times you will see the training data again and again. The LR is, I think, the learning rate. Okay, I think they are using a different kind of optimizer, so we can ignore this B1, B2, and all these things, RW, because that is not covered yet. But the learning rate is important to us, which that is 0.02, that is your eta value 0.02. So what is this doing? Okay, so here they are initializing uh, the weight values of all the layers. Yeah, these four layers, a 1 2 3 4. So for each layer you are initializing the weight. So W is the weight. They are initialized in using this Xavier initialization of weights. So you don't need to know in deep about what this Xavier is, but it is like a well-studied way to initialize weights, because if you initialize all the weights as same, let's say if you put all the weights are same, all W is equal to, let's say, some K, then what happens is when you compute the gradients, all weights will get the same gradients. Like all weights in the same layer will get same gradients. So all weights will be updated in the same manner. So like that can happen if you initialize with some same weight. Or if you initialize with like 0, then what can happen is many of the layers will not get any activation. So in ReLU, if it is not activated, then the gradient for ReLU function is 0. So no back propagation will happen. if you initialize with very small weights or something like that. So this Xavier initialization is a way to kind of initialize your weight such that you get enough activation in the output layer, so that we can ignore. So what they have done is, for each I comma layer, I is the index of the layer, and for each layer they have initialized the weight using this method of Xavier. Then maybe I can just run this. Then for t in range 1 to epochs plus 1, that is for each epoch, what needs to be done is you need to do a forward pass. Like now is the main training part. Training the model means doing back propagation and updating the weights. So you have a forward pass in which uh, you are calling your function, like you're passing through each layer I in range 1 to L plus 1. L is the number of layers that we had defined here. So you're going through each function. If you see, f function takes as input ai minus 1. Ai minus 1 is the activation of the previous layer. Ai is the activation of the current layer. So you are calling like in a for loop, that is one after the other. So this is the forward pass. I think in each f you have stored the layer activation function, like the way I have called you here. This thing has been stored in each of f of I. So that's why fi calls the corresponding layer activation function. So once you go through this for loop, your forward pass is done. Then you have to do back propagation. So in back propagation, what you are doing is you you have to iterate from last layer to the first layer. So the range function, what it does is it gives values from the initial value, that is 1 to L plus 1. But when you put this extra thing, this thing, what it will do is it will start from the last and keep coming back. So it will start from L and then L minus 1, L minus 2, like that till it reaches 1. So you start from there, and if you look at here, there is a D here, and there is a DZ where so this if you see, it is the final layer activation minus the initial layer activation, the difference of it into 0.5. So this is the gradient of the squared error. If you look at this, right, it will be 2 into x minus, like this is basically x minus x bar into transpose into x minus x bar. So if you, in the gradient of this will be x minus x bar 2 times multiplied by 1 by 2. But there is an extra 0.5 here. But this term is what you have is the gradient, this value. This is the loss. And this is dl by dx. So that is back propagated to d into the gradient of the activation layer. So here d is equal to 1 means d is true. So that is stored in dz. Then dz is multiplied to the pre-activation part, because f a ai comes from summation ai minus 1 into your w plus b, right? So here if you compute the derivative of this with respect to this, then you get what you get is ai minus 1 in some form. What you get is this. So the derivative of dz, what you are getting is d into this, and dw you are getting as dz into this. I mean, you will have to look into this carefully, but what it is doing is it is computing the gradient at each of the layer from last to first, this part. And this addendum update you can ignore because this has not been covered, but maybe you can replace it with, but ideally what you will do is, like, based on what you have been taught, this zi will be minus equal to lr times dz, which is the gradient of that particular weight with respect to that weight. Maybe I can just comment this. dzi, and here validation part is you are testing on the test data and then computing the error on the test data, which is the squared mean squared error. If you look at here, this part is the forward pass on the test data. This is same as the forward pass here, forward pass on the test data, and error computation on that. So if you run this, I think this running this may take some time. Again, there is some overflow encountered. I think it is because I changed this value. So maybe I'll switch it back. And now it's running. So I think final output is given in this. What will happen is it will run for some epochs, and then they have shown and they have plotted like the images, the original image that was there in the input, and the 50 dimensional reduction that you did. That is the output of this intermediate layer. That is what is given over here. This thing. Then from this decoder part reconstructed this image, and it is almost as same as the original image. Some plots are blurry, so I'll share this code. You can also go through it and check if you are able to run that. I think there is some, second. Maybe I just run it for one or two epochs and show you the output. If I run it only for few epochs, the reconstruction will not be as good as this. It will be very bad. So I think one epoch is complete. Maybe I'll just wait for one more epoch. I'll stop this and I'll show the output. This was the original thing. If you have any doubts, you can ask. If you are not very much familiar with Python coding, then you may find this kind of overwhelming. But once you get used to it, it's not that difficult to implement your own kind of architectures. But you will require some practice, like just going through these kind of blogs online. You can learn a lot. So I stopped the training after just two epochs. So that's why you're getting very blurry kind of thing. Like this 5 almost got reconstructed as a 3. 4 is very blur like that. But even with just two epochs, it is doing not very bad. It seems okay. It's like this 5 is written very badly. Still it reconstructed it somewhat. Okay. Like the same principles that we have learned, forward propagation, the activation layers, back propagation, that is what has been coded here to be implemented computationally. The weight update part is a slightly different method, but it's somewhat similar. Only some, instead of like, there are some extra parameters apart from learning rate which is used here. But with the standard method also you can do it. Training may take some more time. That is the only thing. These are some specialized methods. Okay, any doubts? And just wait for till 7:50 or something. If you have doubts, then you can ask. Otherwise, you can close the meeting. Okay, then I'll stop sharing and I'll close.